casual are we?
Speaker is Stephen Miller.
So
Stephen J. Miller.
Stephen J. Miller, yes. So even though I'm the speaker, I'm actually really more of a bystander on this project. Most of the work was done by my student Ryan, who unfortunately is not able to be here today. So I will try to do the best I can. So before I go into the details of my talk, there's at least one, if not two, undergraduates here, either in person or by Zoom. I want to make a quick plug for the Polymath Junior program. So a couple of years ago, no, this is being recorded, I don't want to say that. I'll just say that when COVID happened, the math community was very good about pivoting and providing opportunities for students to work online. We've continued to do that. And so if anybody has some students, it's a little bit tough for this year, but for next year, or if you're interested in working on some of these problems with me, please let me know. The slides are online. You can get more details there. But the goal is to try to give as many people as possible, both a research experience as well as an opportunity to mentor people who are getting a research experience. So anybody who has problems or wants to help me with some of mine, please let me know. So, building on some of the talks we've heard today, I think the very first talk in the conference was related to just, sum sets and relating this to some famous problems in number theory. The sum set is exactly what you would expect. Since it's now almost 5 o'clock and it's been a long day, that may be not quite as obvious as early in the day, but we just add all pairs of elements. The difference set is we subtract all pairs of elements. Somebody was mentioning earlier, I think you could do things in 15 minutes. If I asked you, I think in 2 minutes, which set do you think would be larger? I think most people would hop on the difference set because subtraction is not commutative, even though all the pairs of diagonal elements, x will always give you different sums, but they'll always give you the same difference. So few of the times, typically, are we going to be having repeated elements that we expect a typical difference set is going to be larger than the typical sum set. And so just some standard terminology, in Ostraka, we will say that A is sum dominant if A plus A has more sums than A minus A has differences. I think it's recording. Is it not recording? I thought I hit record. No, it's recording. Okay. But it's difference dominated if there are more differences than sums, and balanced if they are the same. And so the first question is, do there exist sum dominant sets? And so a little bit of search gives you one, and I believe this has been proven minimal in terms of girth by Peter Hegarty. Is that right? Okay. And then, of course, once you have one, then you might want to ask, how many are there? Can you find constructive ways to create such sets? And so there's lots of different constructions. You can make infinite families. Unfortunately, we don't have an infinite family construction that has the density of what we expect to be. And I'll say a little bit more about that in a moment. And then this is the second conference in a row in about a week where I'm quoting Mel, hopefully I'm still quoting it correctly, that even though there exists sets A that have more sums than differences, such sets should be rare, and it must be true with the right way of counting that the vast majority of sets satisfies A minus A has greater cardinality than A plus A. And so this is a great statement. It's inspired me and many of my students over time, not just in terms of doing research, but in phrasing things carefully so that when you make conjectures, it's extremely dumb that, it must be true in the right way of counting. Well, if you don't see it, you're not counting right. And so this goes back maybe to some of the conversations earlier about the no dictator law, but maybe dictators should be allowed, and certain people at the pinnacle of their careers should be allowed to determine how we count. And so the question is, what is the right way of counting? So the first candidate for the right way of counting is to just say, let's pick a subset of the integers from 0 to n minus 1 uniformly at random. So all subsets are equally likely to be chosen, and see what happens in that case. There is not a typo on this slide, even though it might look like there is one in the theorem. I have fixed the slides online, so it doesn't have this. I didn't want to download to my iPad. One of the annoying factors of this is you define your set to go from 0 to n, 0 to n minus 1, 1 to n, or whatnot. And so I really should be dividing by 2 to the n, not 2 to the n plus 1, because I'm only going up to n minus 1. But it doesn't really matter because I'm taking the limit and I'm just trying to show it's greater than 0. So it just changes things by a factor of 2. So what Martin and O'Brien showed in 2006 is that if you choose your subsets uniformly at random, then a positive % of the time, you will actually have a sum dominant set. Now, that positive % of the time is extremely small. It's on the order of 10 to the minus 3, 10 to the minus 4, but it is a positive %. And the intuition is that if you look at what's going on, you can split your set into three parts: the left part, the middle part, and the right part. And if you want to look at the sum set, the far left part is coming from left plus left, the far right part is coming from right plus right, and almost all things in the middle are going to be filled in. And so if you really want to see, is it sum dominant or not, it matters what's going on in the left fringe and the right fringe. And so because we're choosing all the elements essentially with probability 1/2, that's another way of looking at this. You give me a prescribed left fringe and a prescribed right fringe, and those have positive probability of happening. And so that gives you some intuition as to why this is actually not a surprising result. So if we rig the fringes, we can definitely make a positive percent. So the question is, what's the right way of counting where we can no longer rig? We want to have fair set construction. And so this is suggesting that the uniform model may not be the right way. So the simplest generalization is, another way of looking at the uniform model was every element was chosen with probability 1/2. Well, let's still choose all the elements with the same probability, but let's no longer say that that probability is 1/2. Let's let that probability be P of n. So we have a nice binomial model, and we will assume that P of n is going to 0 as n goes to infinity. So it's not going to be a fixed constant multiple. And we will assume that n times P of n is going to be much, much, much larger than 1. Another way of saying this is P of n is not decaying faster than 1 over n. If we had extremely rapid decay in P of n, our set would have really no elements. It's really not that hard to prove results about empty sets or sets with 1 or 2 elements. So we want there to be enough elements in the limit so that we have stuff to work with. And so Martin and O'Brien in their paper conjectured that A is not MSTD with high probability. And in fact, you can prove that with 100% of the time, it's not going to be. So with Peter Hegarty, we were able to break things up into 3 different ranges, depending on how rapidly P of n is going to 0. So if P of n is decaying faster than n to the minus 1/2, then it's actually very easy to show that for almost all A, there are twice as many differences than sums. And the reason to think about this is, if my decay is faster than n to the minus 1/2, then I expect to have fewer than n to the 1/2 elements in the set. I have n possible elements, probability of less than 1 over n to that 1/2 for each one. So I have at most on the order of n to the 1/2 elements. How many pairs of sums or differences do I have? It's the cardinality of A squared. I don't care about factors of 2. So if it's less than n to the minus 1/2, I expect fewer than n sums or differences. So I don't really expect there to be many collisions. So I expect almost every pair to give me a unique difference or a unique sum. And so this is the easy range. And we really don't need to use any advanced mathematics to do this. Chebyshev is enough to just trivially bound variances and stuff like that. Things get interesting if you choose P of n to be of size C times n to the minus 1/2. And now, depending on what that constant C is, we get different behavior. And you can write down explicitly what the function is, and there's a nice phase transition that goes on over here. And then if the probability is much larger so that your sets are of decent size, you're going to now start getting a lot of collisions, and now the work is much harder. So I did the easy case. Peter did the hard case using some nice strong concentration results of Roux, and was able to show that there's a nice, so we had a nice talk on palindromes and mirror images earlier. So there's a nice mirror image result here where the number of missing sums is basically twice the number of missing differences when we're in this regime. Okay, so the next question is, how can we generalize this? There's lots of different ways. I'm going to talk about one way now, is what if we consider an arbitrary fixed linear combination? So what I mean here is, let's choose some integers u1 through uh, and let's look at all combinations. So the easiest case would be is if the u's have absolute value 1, then they're either going to be +1 or -1 because they're integers. So I really have just sums and differences. But we don't have to consider anything as restrictive. We could consider the more general linear combinations. And so we want to see what happens as we look at things, and can we say anything about the set of possible linear combinations with this given weight vector u1 through uh. And if I look at different weight vectors, what can I say about the relative sizes? How does it depend on these various things? And the previous work can easily be recast into this. Okay. So things get a little bit harder as we start working in more than two components and with more than just plus and minus one. And it's not immediately clear how to generalize some of the results. The rapid decay, it's not so bad because there's so few things that happen. You don't really have to worry about the collisions. But when you have the collisions, it now becomes a lot of work. And Ryan did a masterful job of doing all the technicalities. I have my clock over here. It is now closer to 5 o'clock than it is to 4 o'clock, which means this is not the time to do technical details. So if you were paying attention, sorry, of course everyone was paying attention. As you were paying attention, you noticed that on the very first page of the slides was a link to the paper on the archive. And there will be some additional slides here that have some of the technical details, but again, this is not the time to go into high level. So let's just do big picture of what's going on. So let's let theta L be the set of all sigma such that if I reorder, I get the same as U1 through UH. So this is in some sense a way of trying to capture how often can I get multiple choices giving me the same element in this L of A. And so if you want to just argue naively, well, I have H components. The probability I choose an element is P of N. So the expected number of elements in my set A is N times P of N. I have H components, so I raise that to the H power. And let's just assume everything behaves as equally as everything else, and I'll divide that by theta of L. And that should give me how many things I expect to have. So this is a rough estimate. The difficulty is dealing with the dependencies that arise. And that becomes a lot more involved, and the calculations become a bit harder. So if I just have two summons or two terms, I just want to deal with 0k can't be an A, 1k minus 1 can't be an A, et cetera, et cetera, et cetera, if I want to avoid k not being an A plus A. And it's not so hard to just look at all of these independently and then deal with, okay, well, they're not quite independent. Sorry, no. Here, these would all be independent. But as I start getting into triples and higher, it's now a lot more involved. And so much more work has to be done. Okay, there's more that can be done. You can also look at Poisson convergence of various things. Again, it's after 440, so I'm not going to go too much into that. I will just state the result we got. In the subcritical range, where everything is very sparse, the result is exactly what you would expect from the naive argument. It's so hard for things to collide that basically almost everything is unique. And so the result is amenable to simple analysis, simple bounding. There is an analog of what I got with Peter in the critical range, where we have this nice phase transition that happens where if your set has just the right number of elements, then fascinating behavior occurs as we vary the multiple of n to the appropriate power. And in the supercritical, when we have a lot of elements, the generalization of how many missing elements you have is a bit more involved. So it wasn't quite as simple as I expected. I think following Mel, I was careful. I went and I checked the older papers I wrote, where we never exactly mentioned what should be going on in this case. So with my student, Vinny Hogan, many years ago, we did the first two cases under the assumption that all the U's were plus or minus 1, and we had nothing that we could say in the supercritical. And since we had nothing to say, I think we were actually very careful, and we did not conjecture in the paper. And I just checked that this morning. I did not see a conjecture. Now, again, if you quickly read Riemann's paper on the zeta function, you don't see conjecture. You just see this throwaway paragraph. Wouldn't it be nice if all the zeros were as symmetric as possible? But after quick effort, I have moved on because it's not relevant to the problem at hand. So I did not read my paper carefully enough to make sure I didn't conjecture, but pretty sure I did not. Okay, so the key tools is basically we need some way to deal with the dependency on graphs that we can associate to the different pairs, triples, quadruples, and higher, and just keep track of how often everything is going on. I don't want to talk too much, but the slides are here if anybody's interested about the values that L takes on. This is something we've seen from other talks today. We know they take on values in a certain range. How many values do they take there? How often does it take on certain values? What can you say about stuff like that? there's results you can show, and you can look at, the total variation between this and Poisson measures, and just show that you have, nice Poissonian behavior. Things are behaving as you would hope. Right. So just, very, very high level, the main ingredients in the proof are asymptotic enumeration, Stein's method, and Jansson's inequalities, and then the Kimbrough-Martingale machinery. So just, a little bit more detail. We need to derive an asymptotic formula for the number of distinct representations. This is related to a bunch of, standard objects, standard enumeration results can come into play. For the Stein's method and Jansson's inequalities, we have to look at these dependent results again, and we need some estimates in the different regions. And then the last, which I think is the most interesting, is the way most of these proofs go. You calculate the expected value of whatever objects you want to compare. And then you need to show some kind of concentration about the expected value. And if the expected values are well separated and the scale is sufficiently small, then you're done and it's very easy. Unfortunately, if the expected values are close to each other relative to the scale of fluctuations, then it's very hard. And then you need to show that it's strongly concentrated. And that's what goes on here. So I think there's enough people in here who can correct me if I'm wrong. I think if you look at A plus A and A minus A is missing, I think, like 7 on average, and A plus A is missing 11 elements on average, something like that. Ballpark, does that sound reasonable? They're both very close in terms of having almost all the elements possible. So if you just choose the uniform model, we expect the set A to have on the order of n elements. I'm sorry, n over 2 elements. But if you look at all possible pairs, the number of pairs is on order n squared. So it turns out almost all of the 2n possible sums are realized. And the number of missing sums is on the order of, I think mine is like 11 that you're missing. And I think the number of missing differences is on the order of 7. And so because these numbers are so close to each other, you need to do a lot of work to show that they're tightly concentrated about those. Because it's possible that maybe I have a large number of sets A, such as A plus A is really, really small, and that drives down the mean, but then I have a good positive percent of the time when A plus A is actually going to exceed A minus A. And so when you want to try to prove how often can stuff like this happen, you need some control over how concentrated things are. And that's where the Kimbrough-Martingale machinery comes into play to get these nice, strong concentration results. So there's a lot of additional problems that can be done along these lines. Some of them are going to be a lot more technical than others. I haven't done things in higher dimensions in a couple of years, so I think it's time to start looking at higher dimensions again. Can you take these results and apply them to different lattices? And so, we have both the standard integer lattice, but you could also do a hexagonal lattice and see how does the lattice structure affect what goes on. I've done some work with students over the years with stuff like that. Another thing is you could look at other settings than the integers. We could look at groups. And so if you look at the clock groups, what's nice or what's not nice, depending on your point of view, is there's no longer a fringe. And so in those settings, it's a very different problem than in the integers. And I believe in the limit, almost every set is balanced when you look at it in the clock groups. And so you could try doing stuff like that over here. There's a lot of other more technical stuff you can do if you love delving into stuff like that. I am fortunate that I have a lot of students over the years who love delving into stuff like that. So thank you.